Hello and welcome to this Ansys Innovation course on aerodynamics of an FSAE car. In the previous lesson, we understood how to transform the complex FSAE geometry to the simplified CAD and clean up various components using Ansys Discovery to arrive at the CFD-ready CAD. This lesson will focus on generating the mesh for the cleaned CAD model. A good quality mesh is critical to ensure that we get a properly converged solution with accurate results. Since this is a complex CAD, special care needs to be taken at various parts during meshing. For this tutorial, we will be using Ansys Fluent's watertight workflow meshing to mesh the model. Sounds interesting, right? Let's get started. Launch Ansys Fluent in meshing mode. Make sure that double precision is enabled. You can set the number of processes based on your license and computing resources under the parallel section. For this case, we are going to use 16 processes. Set the correct working directory and click on Start to launch the meshing mode. Under Workflow, select Watertight Geometry as shown here. The watertight geometry workflow consists of a series of tasks arranged in a proper order for ensuring smooth and hassle-free mesh generation. Import Geometry task is by default the first task of the watertight geometry workflow. Here, we will keep the units as mm. Select the provided CAD file to import the CAD as shown here. We import the geometry file as a .pmdb geometry file generated in the previous lesson for CAD import, as it is much faster to read a PMDB geometry than the original CAD geometry. Another advantage with the PMDB file is that it is operating system independent, meaning you can move your workflow into a Linux environment without any issues. Here is the imported CAD. We need a refined mesh in the vicinity of the geometry to properly capture the complex fluid flow behavior in this region. So, we need to employ a local mesh refinement. One way to do this is by creating body of influence (BOI) objects at the CAD level itself. But in this lesson, we will learn another method in which local mesh refinement can be done directly in the watertight geometry workflow using the Create Local Refinement Regions task. By default, this task is not visible in the workflow. In order to enable it, right-click on the Import Geometry task, insert New Task and select Create Local Refinement Regions. Here we will set up local refinement regions around both wheels and rear wing. The primary function of the rear wing is to generate downforce which pushes the car onto the track, improving its grip and helping achieve cornering speeds. Rotating wheels create a significant disturbance in the airflow, resulting in the generation of lift and enormous amounts of drag. To accurately predict the impact of these parts of the geometry on aerodynamic forces, fine mesh resolution is required. In the Create Local Refinement Regions task, give an appropriate name, enter the mesh size as 16 mm and select the front wheel label. Adjust the box parameters so that a small area downstream of the wheel is also included and the wheel center is at around a third of the length of the box in the flow direction as shown here. Leave the rest of the settings to default and click Create. Similarly, create a region around the rear wheel. For the rear wing, let all the settings be the same except for the box parameters. Since the wing significantly deflects the airflow, we need to have a slightly bigger refinement area as compared to the wheels. Enter the parameters as shown here and click on Create. In addition to creating downforce, the rear wing is also responsible for a large, complex turbulent wake region. Because of its impact on the drag generated by the car, it is critical to capture the flow dynamics in this region as accurately as possible, which requires a fine mesh resolution. For this, we will have 3 local refinement regions around the whole car where the mesh size will gradually increase from a small value in the inner zone to the global mesh size in the outer zone. Now let's create these refinement zones. Considering the dimensions of the car and the enclosure, we have determined the XYZ coordinates for defining the box. Give a suitable name and change the coordinate specification method to directly specify coordinates. Set the mesh size to 32 mm. Enter the following coordinates to ensure that the entire car is covered and there is a small gap of around 1 car length downstream of the car. We can see that a preview of the box is being shown in the graphics window. Confirm that the box is correctly placed. And click on Create. Repeat the process for subsequent refinement regions with a mesh size of 64 mm and 128 mm respectively. For subsequent regions, it is generally recommended to increase the downstream length of the region by 2 car lengths, the height of the refinement region by 1/3 of the car length, and the width by half the height of the region. Moving on to the third step to locally refine the mesh for accurately capturing the complex geometrical features, change the "Would you like to add local sizing" option to Yes to add the local sizing. Here, under Size Control Type, select Curvature. This type of local sizing is used to capture the complex curves present in the geometry. Give an appropriate name to this local sizing and enter the min and max size as 1 mm and 64 mm respectively. Set the Scope to Faces and Edges. Change the curvature normal angle to 12 degrees. Select the label Chassis so that the entire portion of the car, including the intake and exhaust systems, is selected, ignoring the wheels, wheel patches, wings, and the diffuser. Leaving the rest of the settings to default, click on Add. We will similarly create another curvature local sizing for the front, rear, and side wing and the diffuser. All of these elements need finer mesh settings so that the geometry is accurately captured, as these have a direct impact on the aerodynamics force generation. For that, select the appropriate labels, give a suitable name, and enter the min and max size as 0.5 and 8 mm respectively. Ensure that the Scope 2 is set as before to Faces and Edges. The leading and trailing edges of the wings are the most critical sections of this geometry selection. The curvature of these features needs to be properly captured, and hence set the curvature normal angle to 9 degrees and click on Add. Finally, we will add another curvature sizing to the front and rear wheels and the respective MRF zones. The MRF zone for the rims of the tires is another important geometrical feature, as it is the reference frame for the rotating wheels. Select the labels as shown here. Enter the min and max size as 0.5 and 32 mm respectively and click on Add. Now that we have the local sizings and the local mesh refinements defined, let us generate the surface mesh, which is the next task in the workflow. Under this task, we need to first specify the min and max size. For that, enter 2 and 256 mm respectively. Make sure that the Scope Proximity to option is set to Faces and Edges. The cells per gap setting defines the division of gaps into the specified number of cells with a higher value, leading to a more refined mesh in the gaps. For this tutorial, we will keep cells per gap and all other settings to default and click on Generate. The generation of the surface mesh will take some time depending on the number of processes used. Once done, this is how the mesh should look like. First, let's check the mesh quality. In the console window, maximum skewness of the mesh is printed. We can see that the current value is 0.95 while the recommended maximum skewness for such a simulation is around 0.7. To improve the skewness, right-click on Generate the Surface Mesh and insert the Improve Surface Mesh task. Set the face quality limit to 0.6 and click on Improve. Once done, the maximum skewness is again reported in the console. We can see that the value is now 0.6, which is acceptable. Let us now move to the next task, which is Describe Geometry. Since the geometry we have imported consists of 3 fluid regions and no solid regions or voids, for geometry type, select the geometry type consists of only fluid regions with no voids. Also select Yes for Change all fluid boundary types from walls to internal. Leave the rest of the settings to default and click on Describe Geometry. The next task is the Update Boundaries task. Based on the named selections defined during the CAD phase, the boundary conditions should be automatically assigned to the appropriate boundary. Make sure the inlet, outlet, symmetry, internal and wall boundary types are assigned properly as shown here and proceed to the next task. For the Update Regions task, before clicking Update, check if the 3 fluid regions are defined, 1 for the fluid enclosure and remaining 2 for the MRF zones. Now that the surface mesh is generated and the geometry is defined, we will proceed to the next task, which is the Add Boundary Layers task. The boundary layer is the fluid region near a wall where the viscous forces are significant. Understanding the boundary layer behavior is critical since the aerodynamic force generation, especially from parts like the front and rear wings, is greatly dependent on the characteristic nature of the boundary layer. The boundary layer mesh should be thick enough to capture the entire physical boundary layer thickness and also fine enough to capture the dynamic gradients inside the boundary layer. The boundary layer mesh resolution is generally discussed in terms of Y plus and the number of layers. Y plus is a non-dimensional distance between the wall and the first mesh cell. A deep discussion on boundary layers and the required mesh resolution is beyond the scope of this course, but for our purpose it is sufficient to know that Y plus close to 1 with enough mesh layers will result in a very accurate capture of the boundary layer physics, but will result in a significant mesh cell count. On the other hand, a large Y plus with too few layers will result in a poor resolution of the physical boundary layer. For external aerodynamic cases using RANS CFT methodology, a Y plus of around 10 with 5 to 10 layers is a good compromise. For our simulation, we will enforce a Y plus of 40 and set the number of layers to 6. Note that the choice of turbulence model also determines the Y plus that one can use. Let's now see how to add the boundary layer mesh with our chosen parameters. Select Yes in the Add Boundary Layers task. Set the offset method type to last ratio. This method is very widely used for external flows as it gives control over defining the first cell height, which is a direct effect on the Y plus. Note that the input for this method is the first cell height and not Y plus. The first cell height can be calculated from Y plus by using the formula as shown here. The density and molecular viscosity are known for the fluid, which is air in our case. The friction velocity can be calculated from the Reynolds number, wall shear stress, and skin friction coefficient with the empirical relations as can be seen here. Assuming a velocity of 35 mph or 15.65 meter per second and a Y plus of 40, we get the first cell height to be 0.98 mm. For convenience, let's use 1 mm. Give a name, enter this value and set the number of layers to 6. Select the labels under Grow On as shown so that the entire car geometry is selected. Make sure under Add In, Fluid Regions is selected and click on Add Boundary Layers. Now let's add another boundary layer for our MRF zones. Keep the same settings as the previous boundary layer. Select the zones under Grow On as shown and choose the 2 MRF zones. Click on Add Boundary Layer. Now that the boundary layers are added, we are ready to create the volume mesh using the Generate the Volume Mesh task. We will select Polyhex Core under the Fill With option. This mesh type generally results in a lower mesh count relative to the polyhedral mesh, thereby reducing the simulation time. Enter the min and max value of 2 and 256 mm respectively. Click on Generate. Once done, we can check the quality of the volume mesh in the console window. For a good mesh, the minimum acceptable orthogonal quality is 0.1. As can be seen, the current mesh does not meet the requirement and so, we need to insert an additional task to improve the volume mesh. Right-click on the Generate the Volume Mesh task and select Improve Volume Mesh as shown here. We will set a cell quality limit of 0.2 and click on Improve. As can be seen in the console, the orthogonal quality reported is now accepted. Now that the mesh is generated, it is necessary to make sure that there are no warnings or errors. For that, we need to perform a mesh check. Under Mesh on top left, click on the arrow next to Check and select Perform Mesh Check. Once the mesh check is completed, we can see some information printed in the console. Though there are no issues with our current mesh, we will discuss how to deal with situations where you may experience warped cells or stair stepping. It is possible that the mesh you created might have warped elements. Warpage is applicable only to a 2D element with 4 faces, that is a quadrilateral. Warp is a measure of the deviation of a quadrilateral element or face from its plane. Elements with a high warp will lead to a distorted mesh which is not desired. Thus, the mesh must be adjusted to remove these faces with warp over 0.5. In Fluent Meshing mode, we can improve the warpage by going to Mesh on the top left as shown here. Go to Tools and select Auto Node Move. Change the quality measure to warp as shown and tick the box next to Improve Warp. Select all the boundary zones, set an appropriate number of iterations and click Apply. It will be reported in the console that there is no face over warp criteria. If we are unable to improve all the warped faces, we can increase the number of iterations and try again. We can perform a mesh check again to confirm that there are no warnings. Sometimes, after the generation of the mesh, we may also get a warning related to stair stepping at specific locations on the mesh. This issue arises if the meshing algorithm is unable to create the boundary layer mesh at specific locations according to the provided settings. The location where stair stepping has occurred can be marked by going to Quality under Mesh and selecting Diagnostic Tools. In the dialog box, under Issue, select Stair Step Locations and click on Mark. Depending on the location, we can either ignore this warning if it is not going to affect the results or resolve it by locally refining the mesh at these locations. Lastly, you can also visually check different parts of the mesh to understand the different refinements and ensure that all the complex geometrical features are captured by the mesh. To summarize, we saw how to generate a high quality mesh using the Ansys Fluent Meshing watertight geometry workflow. In that, we understood how to locally refine the mesh around the car using the local refinement regions task. Then, we learned how to add local sizing to ensure the mesh is able to capture the complex geometrical features. After that, we saw how to decide on the y plus value and the boundary layer settings to accurately resolve the mesh near the walls. Finally, we learned the different quality checks to ensure a good mesh is generated and how the surface and volume meshes can be improved. That brings us to the end of the lesson.